Namaste. Okay, guys, today I'm going to present a lesson on the laws of motion. All right. Um, okay, so this is kind of a general, again, for all my classes, but I also want to mention the technical physics class or the VOTEC physics class. So especially you guys, pay attention to this because, again, you're going into a certain trade that fixes and works on vehicles, and vehicles are subjected to forces. And so, in order to be a good technician, and let me use that term technician, you kind of have to know some technical things, hence the term technician. All right. And so the laws of motion, you should have a basic understanding of Newton's laws of motion, because they certainly apply to vehicles. All right. The engineers who design vehicles are educated in the laws of motion. They have to be, in order to design these things. Vehicles are things that we design to control forces in nature, like the combustion process of volatile fuel, like gasoline, or something like that. And obviously they are subject to forces too, forces of friction, all right, air friction between the road and the tires, okay, and so on and so forth. So you really, in order to be a good automotive technician, you should have a decent understanding of Newton's laws of motion. So make sure you're taking notes on this, okay, and make sure you know these laws and you understand each of these laws, okay. So here we go. First, I want to start off with the concept of a force. All right, I did another video on force versus pressure. And I'll leave that for that second video. But just to go over what a force is something that causes an object to accelerate. You not just the simplistic freshman or middle school or elementary school definition where we teach little kids that a force is a push or a pull. That's a little simplistic for this class, all right? And that's not really what a force is. A force is an entity or something that causes an object to accelerate. And I know I'm being a little vague there when I say an entity or something, but the reality is when I'm doing that, I'm kind of butting up against the limits of science, which you ought to know about also, that science, human knowledge has some limits to it. For example, gravity is a force. We don't really know what gravity is. We know how it acts. We know what it does. We can write equations for it. We know that it's somehow caused by mass, like this planet creates gravity, the sun creates gravity, whole galaxies create their own gravitational fields, but we don't know how they do it. So that's a limit to our knowledge. So suffice to say, a force is an entity. It's something that causes an object to accelerate. And it can take many forms, okay? So it could take the form of something invisible like gravity or invisible like magnetism, but it doesn't have to be. Obviously, if you push something with your arm, you're causing a force on that object. So it could be that simple too. I don't want to get too deep into that, but I just want to tell you what the actual definition of a force is. So it causes something to change what it's doing. That's what acceleration means. Acceleration is not a speed. Acceleration is a change in an object's motion. Okay. Um, okay, I guess I got this, just the diagram of the pistons, because what winds up happening is when the fuel is combusted inside the cylinder, the gases create a pressure on the walls of the cylinder, and in accordance with the other video on force and pressure, the pressure creates a force, and pressure is not force, it's related to force, creates a force on the piston, pushing it, down or up, or whichever way the piston is facing or going. Okay. All right. So forces, what you need to know about them is they are vectors. Okay. They are measured commonly in America in pounds. A force, it's a very old measurement. but we as Americans kind of understand what a pound is. All right. If you want to go bigger than a pound for something bigger or a more powerful engine, like a rocket engine or a jet engine, you might want to talk in terms of how many tons of force it can generate. I think in the last video, I said this, and I'll say this again. If you haven't watched that video on force and pressure yet, I have a log splitter at home because I have a wood burning stove. We burn wood, and that log splitter, the hydraulics on it, it's rated at 12 tons of force. Why? Because 24,000 pounds is kind of a big number, and so it's just kind of easier to think of the number 12 tons. All right, it's kind of a moderate log splitter or whatever. They go up into the 20-ton range and so on. But all right, in the metric system, a force is measured in something called a Newton. And I want you to know, because you are an American, you think in terms of pounds like I do. That's kind of what we grew up with here in this country, that a Newton is about a quarter of a pound. So you have like a reference frame for what a Newton of force is. Newtons are not really used that much. Yeah, they are the metric unit of force, but even around the world, because they are kind of a small unit, like if you go to Canada, when you step on a scale, you're not going to measure they don't use newtons on the scale. Instead of pounds, they use kilograms, which is a unit of mass, but mass is related to weight. The more mass you have, the more you weigh. So it doesn't really matter whether you use mass or weight when you're, kind of trying to see, your size and all that. So, and just so you know this too, I'll just mention it, like 1 kilogram of mass, and it doesn't matter what matter you're talking about, whether it's a kilogram of water, a kilogram of steel, a kilogram of lead, 1 kilogram of any matter on the Earth's surface weighs about a little over 2 pounds. 2.2 pounds is what a kilogram is. And I'm just mentioning that so you have kind of a reference frame in your brain of what these things are like and how they relate to each other. Okay. I want to talk about the concept of a net force. A net force is, you can see the definition there. It's a single force that could replace all other forces on an object. So for example, if I'm pushing on something, if I'm pushing to the right, or actually to my left with 4 pounds of force, and at the same time I'm pushing back with only 3 pounds of force, I have a net force of 1 to the left. Okay, 1 pound to the left. That means that 4 pounds this way and 3 pounds this way is the exact same equivalent of pushing with 1 pound that way. So we would say the net force is 1 pound to the left. Okay, and that's it. It's a pretty simple concept. Concept of weight is that what we refer to as weight is the force of gravity on you, on your mass, on the Earth's surface. Okay, so we kind of give that force, weight, a special name, but weight is caused by the force of gravity. Difference between weight and mass is that weight, it's caused by gravity. Mass doesn't need gravity to be mass, and your mass doesn't change depending on where you are in the universe. Not that any of you guys are going to take a trip to the moon or to Mars anytime soon, but whatever your mass is, whatever your weight is on Earth, if you did go to the moon, your weight would change. Why? Because the moon has gravity, but it has less gravity than the Earth. So, for example, if you weigh 100 pounds on Earth due to the Earth's gravity, and you went to the moon, you would still have the same mass, but you would only weigh, if you stepped on a scale on the moon, about 16 pounds. Okay, so weight changes depending on where you are. Mass does not. Okay, normal force, and let me get this video out, that out of the way. The normal force is the name that we give to the force of a surface that's pushing up on something. So right now, you're sitting in a chair, or you're standing, or I'm sitting in a chair right now. My weight is pulling me down towards the floor. Why am I not on the floor? Because the chair is in the way, and the chair is producing the integrity of the chair is producing a normal force counteracting my weight. And yes, inanimate objects can produce what are called reactionary forces or normal forces. Happens all the time. When you stand on the floor, the floor produces a normal force which pushes up against your weight and balances it out, cancels it out, and thus you don't fall. So your net force when you're standing on the floor between your weight and the floor is zero. Let's say again you weigh 100 pounds, you would have 100 pounds pulling down. The floor would produce 100 pounds normal force pushing up on you, and you would have a net force, to go into this expression that we just talked about, of zero. When two forces do cancel each other out, like when you're standing on the floor, we have another term for that, and we say that the two forces are balanced. So in other words, if you have a net force of zero on an object, that doesn't mean you necessarily have no forces on an object. It just means that all the forces on the object cancel each other out. Okay, so the net force is zero, or the forces are said to be balanced. Okay, and those are those concepts. All right. Pressure is related to force. I know I did a separate video on pressure and force, but it's good to get it again because these are two important concepts that everybody screws up. Okay, pressure is not force. It's related to force. Okay, so if we are in class at some point, and I hope we are because I'm tired of making videos from my bedroom here, and you start to say, and I start to ask you to describe what's going on, you're like, well, the pressure of the force of, and you start to screw it up, I'm probably going to correct you on that and say like, whoa, you're in a physics class here. You know the difference between pressure and force. What is going on? All right. And you should, especially if you're going to be an automotive technician or something, you really ought to know some, again, the word technician, you ought to know some technical knowledge. And this bit of technical knowledge is kind of important. It's kind of basic. Pressure is not force. It's related to force. Pressure is a force spread out over an area. Okay. So the area has a definite effect on the pressure. So if notice it's on the bottom of the fraction here. And so what that means is if this number gets bigger, the surface area gets bigger, the pressure goes down. So if you take a weight and, like a weight from a weight set and you put it, on the floor, okay, it produces a certain amount of pressure for that weight for that surface area that it's on the floor. If you took the same weight and welded a nail to it and then put it on the floor, you probably would make an indentation in the floor or something. Why? Because now you're taking that same weight force and you're focusing it down instead of spreading it out over the area of the metal weight. You would focus it down on a thin point. Okay, and let me just have a pencil right here. You would focus it down on a small point, which would increase the pressure that weight is exerting on the floor. Okay, causing it to indent or whatever. Okay, so here's a good picture to illustrate. Here's some dude doing something that I would never do. People can do this. All right. This is the old bed of nails trick. There are videos on YouTube on this. All right. Just YouTube bed of nails, and you will see on YouTube videos of people walking on beds of nails, laying down on beds of nails. And, as amazing or crazy as that sounds, it actually is not the force of your weight that comes into play here. It's the pressure that your weight exerts over the surface area of the bed of nails. So, for example, the reason why this guy can stand on this bed of nails, which again, something I know I've seen people do it, but I don't think I ever want to try it myself. All right, is because he's not just standing on one nail. He's standing on, 50 to 70 nails under the surface area of his feet. So his weight is not focus. Now, if he were to stand on one nail, that would go right through his foot. But if you take and you spread that weight force over 70, 80, 100 nails, all right, it goes down 70, 80, 100 times, or however many nails you're dealing with. So the more nails you have, the more that weight force is getting spread out. And that's a good way to illustrate the difference between force and pressure. If you only had one nail or so, his entire weight would be focused on the very small surface area of that one nail, and that would probably push through the guy's skin, all right, and into his foot, and would be very painful. But if you spread it out over many, 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 many nails, even though the nails are, pointy and kind of sharp, all right, it's not going to hurt you, okay? Just for the record, and I'm getting this on video, don't try this, okay? Because I do not want to get any call from parents, all right, saying, my kid, because he was watching, a video you made, tried to stand on a nail or a couple of nails. Don't make a bed of nails, all right? So just saying that. But this illustrates the concept of force versus pressure, okay? All right, pressure is measured in PSI, which is the British unit. We use that in America, pounds per square inch. Okay, you see this on your tires and all that. Tire pressure is pounds per square inch. And what that is that the air inside is pressing out over the surface area of the inside of the tire with a certain pressure, okay, that the tire is rated for and designed for by the engineers who designed it. Okay, and they measure that pressure in pounds per square inch. In the metric system, they do a Newton per square meter, and 1 Newton per square meter is known as a Pascal. The symbol is PA. That's a really small unit of pressure. So oftentimes, people, or engineers, when they're designing using the metric system, they, instead of using pascals, would use kilopascals. A kilo, the word kilo means 1,000, like in kilometer, which is 1,000 meters. So a kilopascal is 1,000 pascals. So, 30 kilopascals would be 30,000 pascals. So rather than use 30,000, they would just say 30,000 kPa or something like that. All right. So it's just a little more convenient of a unit to use. All right. So when you're using the metric system anyway, but we're not going to really use those too much in this class. Okay. Here is the reason why I have this is to illustrate the concept of the first law of motion called inertia. What you're looking at here is, okay, so here's a cannonball, and here's a modern day cannonball. What you're looking at is not a missile. That's a big depleted uranium spike called a Sabo round that comes out of our M1 Abrams tanks. It's an anti-tank round. It doesn't explode. It's just a big, heavy dense piece of metal. It's much denser than steel. It's actually denser than lead. Depleted uranium is. And it's oftentimes referred to as an inertial round. It's basically just a modern day cannonball. And the concept of inertia is a property of matter, and write this down. It's a property of matter whereby the matter does not want to change what it's doing. So what does that mean? That means if you're at rest, you don't want to start moving spontaneously. If you are moving, you don't want to change how you're moving. You don't spontaneously speed up, slow down, or turn, not without a force involved. So on Earth, it seems like things change all the time, what they're doing, and that's because there are forces all over the Earth. If you take a softball and you chuck it on planet Earth, it goes through a lot of motion. It changes what it's doing all the time. It doesn't just go in a straight line. It goes for a bit and it curves, and then it hits the ground and it rolls for a while and stops. Why? Because it curves because gravity stops its flight from going up, forces it to curve, go into the ground. Once it hits the ground, the force of friction causes it to stop. So you have several forces causing it to change what it's doing. But if you take the same softball and you were in a spacesuit and you chuck the softball in outer space, far away from planets and stars, where gravity is like nothing, that softball would just keep on going. And we keep on going forever and ever. It would go once it left your hand, it would leave at a certain speed. It would not speed up from that speed. It wouldn't slow down because there's no air friction to stop it. It wouldn't spontaneously turn. It would just go straight. Okay. And why? That's due to the property of inertia. The more inertia you have, the more you want to do this. Okay. So, okay, here's a good illustration of a concept of inertia. This guy has a lot of mass. This little dude right here has a little bit of mass, right? If you can imagine walking into this sumo wrestler like this, he's got a ton of inertia, all right? So you walk into that guy and he's just standing there, right? You're going to lose, right? You're probably just going to, like walk into him like walking into a wall, and you're probably going to bounce right off, and he's probably not going to move. Okay, why? Because he has a lot of inertia, because he has a lot of mass. And so his inertia, because he has a lot of it, really wants to keep him from moving. It takes much more force, because he has a lot more inertia, to move this guy, obviously much more than this, tiny little guy has. Now, this little guy, not that you should go walking into children, but if you did, you probably wouldn't bother you that much, or hurt you. It would bother the child, I'm sure. But because the small guy here doesn't have a lot of inertia. If you're on the football team, you certainly know this, right? You run into the quarterback, nobody's worried about sacking the quarterback, because the quarterback is usually not the biggest guy on the team. But if you were to, run into a linebacker, and linebackers tend to be bigger, all right, you're going to know it, because the linebacker, because they have more mass, has more inertia, more resistance to changing their motion. Consequently, also, when the linebacker gets, you much rather, be tackled by the quarterback, not that quarterbacks tackle people, but you'd much rather, be, hit by a quarterback, because they don't have as much mass. And so their inertia, they can't generate as much inertia when they run into you like that. But a linebacker, when a linebacker gets up to speed, they're a freight train, right? Because they have a lot of inertia. And once they're up to speed, they want to keep on going because of their inertia. Okay. All right. So here are the three laws. First law is called the law of inertia: an object that remains at rest. An object at rest remains at rest. An object in motion moves at the same speed in the same direction, unless it's forced by a force to change what it's doing. Sorry, it's the middle of August and there's pollen in the air, so I'm doing a little bit of throat clearing and coughing and stuff. Just bear with me on that. Okay, and that's the first law. And when you were a freshman, you were probably taught this. I definitely know, if I had you freshman year, that you did learn this. Okay, the second law is relates force with acceleration. So the acceleration of an object gets bigger with the force that you push on. So if you push on something more, it accelerates more, it changes what it's doing. So if you take a softball and you just chuck the softball with your hand, it's going to accelerate. It's only going to accelerate so much, okay? Because you can only generate with your body so much force. But if you took the same softball and you put it in the tube of a 155 howitzer with some propellant behind it and blew it out of the front end of the tube of that howitzer, that's going to be a different effect. Now, if you chuck the softball at someone and hit them, that's one thing. But if you took the softball and blew it out of that howitzer, even though it's a softball, it's probably going to wreck that person. Why? Because the force generated by the explosion inside the howitzer is much greater than the force that you can generate with just your arms chucking the thing. So the bigger your force, the more it accelerates. Smaller your force, the less it accelerates. The acceleration of an object, there's a second part of this, gets smaller with mass for a given force. So, for example, all right, if we go back a couple of slides to these dudes right here, what we mean by the second law is, okay, so for the force that you can generate, okay, when you push something, all right, if you push the kid, now, again, I'm not advocating pushing a kid, so don't go testing this out on your younger sibling, all right. But if you push this guy right here, this little dude's going to go flying. For the same amount of force, you push this guy over here, he's hardly moving at all. All right. And that's the second part of the second law, that mass also has an effect on acceleration. It's harder to accelerate something that's more massive. It's easier to accelerate something that's less massive. Now, in terms of vehicles, right, what that means is the bigger the vehicle you have, the bigger the engine you have to have in it in order to get the thing to move. All right. Back in the old days, in the 1970s, cars came standard with 8-cylinder engines. And these are big engines, all right? We don't really use these too much today, unless you're in like a truck or something like that, all right? And they burned a lot of gas and they generated a lot of force. They had to. Why? Cars were bigger, because back in the proverbial day, when I was a child in the 1970s, gas was cheap and there was plenty of it. And, no one cared about, how much gas you burned. It was not that big a deal. It was only a few cents a gallon. It was like, 50 cents a gallon or something like that, and was easily affordable. And so Americans built, if you Google cars from the 1970s, you'll see that these were big, big cars. All right. The car I learned to drive in was a 1976 Ford LTD, which was a size in length. It was like the size of a modern day F-150 pickup truck. And I'm not kidding you. All right. Why? Again, gas was cheap. There was plenty of it. So the car had a lot of mass to it. And so we needed bigger engines to move those cars, but we just didn't care at the time. Now we do, because gas is more expensive. And there's the environmental factors and stuff about burning gas and stuff. So Americans, when the price of gas went up, demanded smaller cars, but they wanted the same speed. So how do you get a burn less gasoline, but get the same sort of speed? Because Americans don't like to go slow. Well, you have to make the mass smaller. In other words, you have to make the car smaller. So cars got smaller. And, also we developed lighter alloys and we put plastic in it and stuff and things like that in order to make the mass of the car smaller. Okay. So that's the second law. Third law is action reaction. And what you need to know is that forces are created in pairs. So when I push on something, the something pushes back on me automatically. Okay. It reacts with a force so when I push on a wall with 10 pounds of force, the wall, if it can withstand it, if its integrity can withstand it, pushes back on me with 10 pounds and cancels out my force. It pushes back on me, we would say a normal force of 10 pounds, and pushes back on me. All right. And that's action reaction. And this happens all the time. In terms of vehicles, where the third law is between the tires and the road. Between the tires and the road, there's a force of friction. And don't believe me? Try pushing a car when it's in neutral. And the wheels are not and the transmission doesn't allow, or not when it's in neutral, but when it's when it's like in gear, when it's like in drive or something like that, but not moving. Try pushing that thing. You're not going to do it because the wheels won't turn, and the force of friction between those tires and the road is absolutely immense. Okay, when the wheels turn, what's actually happening is the force of friction, all right, the wheels push against the force of friction in the road, and the force of friction, equally and oppositely, pushes back on the wheels, and the car goes forward. This happens all the time. If you've ever been swimming, what do? You take your hand, you put it in front, you cup your hand, you put it in front of you, you kind of cup some water, and then you draw it back. Why? Because what happens is you're actually pushing on the water as you draw it along the length of your body. What is the water doing? Well, the water has mass. Water has a lot of mass. 80% of your body is water. 80% of your weight is water. So when you push when you push on the water pushes back on you and you go forward. Okay. If you've ever been in water and you're floating and you go and push on your buddy just to do whatever, yeah, that your buddy moves backwards, but you move back also. That person's inertia generates a reaction force. So when you push on them, their inertia pushes back on you equally and oppositely, and they go forward, but you also go back. Okay. So that's the third law. Think of if you've ever shot a firearm like that, the force created by the explosion, the charge inside the firearm, shotgun, handgun, whatever, rifle, the force generated by that propellant goes in all directions. So the tube absorbs it on the side and kind of cancels it out. The barrel does, but the bullet goes forward. The bullet, according to the first law, because it's at rest, doesn't want to go forward and has some inertia, a little bit of inertia because it's small, but it reacts to the propellant force pushing it forward by pushing back. And what happens? That means the gun recoils. Okay. So, and if you've ever shot a firearm, especially like a 12 gauge shotgun, there's a decent amount of recoil in that. You can't just lackadaisically stand there and shoot a shotgun. You have to have a decent stance or that thing's one, either going to fly out of your hands, or two, knock you on your rear end. All right. Because the force, according to the third law, on the shot or the bullet will push back on you and you get a recoil. Okay. So those are the three laws. Okay. Here's the example of the law of inertia like that. So what happened here in this? Why is this guy stuck? Well, because what happened was probably what happened was we're on a icy or snowy road where the force of friction goes way, way down. And the guy maybe tried to take a turn and tried to stop or something. And the force of friction between the tires and the car, because of the snow or the ice on the road, suddenly went way, way down. And so what happened is the car probably went forward in accordance with Newton's first law. It went in a straight line, constant speed. The only problem is the road curved, and what was in the direction of that straight line was probably the road embankment, or the snow on the side of the road, and the guy went forward and then hit the snow. Okay, because the car was moving and wanted to keep on moving, and the force of friction wasn't there as a controlling force to keep it in a curve, and so the car went straight and then hit the embankment. Okay, here's an oil tanker. These are some of the largest vehicles made by human beings, if not the largest vehicles made by human beings. And these things have a ton of inertia. When one of these things filled with oil goes into like the Port of Providence or something, when these things are up to speed at whatever, 30 knots or 35 knots or that, probably more like 25 knots. All right. These things will literally cut their engines, if they're going in the Providence, like probably shortly after like the Newport Bridge or the Jamestown Bridge or something like that, and then coast in. And they could literally coast for miles. Why? Because they have a ton of inertia. So once these things do get up to speed, they keep on going. All right, because the water provides resistance, but not a ton of resistance. All right, and its inertia carries it forward. Consequently, too, let's say, an oil tanker, like here's the dock, here's the front of the oil tanker, and here's you in between, and the oil tanker is like moving really, really slowly. You're going to be jelly, all right? Because even though it's moving really slowly, the thing's going to have so much inertia that your little force that you exert on it is not going to change its motion at all. And it's just going to keep on going and going and going and squish you like a bug. All right. So why? Because there's a lot of inertia. All right. Second law. Here's a Hyundai Accent. I want to say this is an Aston Martin. Both cars they're both small cars. I mean, they're not large cars. Aston Martins are like one of my favorites because James Bond drives an Aston Martin. And but the two cars have about the same mass. But the engine in the Aston Martin has a heck of a lot more horsepower, which means it can generate a lot more force, all right, than the engine in the Hyundai. The Hyundai is not, made to go fast. It's made to be economical and save you gas mileage and stuff, but not so the Aston Martin. So if you put these together on the line like that, and then the light turned green, the Aston Martin, because its engine can develop a heck of a lot more force on that vehicle, will go from 0 to 60 much. In other words, it will accelerate. It generates a much bigger acceleration than the Hyundai does. So that's the deal with that. So there's your second law. So the mass is the same, this one has a larger force, so it generates a larger acceleration. Okay. Now, if I wanted to get um, a bigger acceleration from the Hyundai, all right, or actually from a smaller vehicle, as the Aston Martin, if I had the Aston Martin go up against like a motorcycle, well, that's a different story. All right. Because why? A motorcycle, with a decent size engine on it like that has very little mass compared to a car. Right. So if you put a motorcycle, a decent like racing bike or something, on the line next to the Aston Martin, now the mass part of the second law is becoming a factor, and the smaller mass, because it's a smaller mass, for a given amount of force will accelerate more. So that's that concept there. Okay, here's action reaction. We already talked about a shotgun or a firearm. Here's another one. Here's a missile. It's like a Triton missile coming out of one of our boomer submarines, all right, like this intercontinental ballistic missile. But what's going on with the missile is, if you notice, obviously the missile is going forward into the sky. Well, where's your action reaction there? Well, look at what's coming out the back of the missile. You see like all this fire and stuff. That's the exhaust. What's happening is fuel is being burned in a combustion chamber. And kind of like the firearm, as the fuel burns, okay, it's kind of canceled out because it's designed to by the tubular body of the sideways, force delivered by the combustion process, kind of canceled out by the shape of the tube of the combustion chamber, but not so much but it's allowed to go out the back. So what happens is it gets thrust out the back. These hot gases get thrust out the back, but they react against the body of the missile. And so the gases go one way, action, the missile gets forced in the other way, reaction. And so that's a good example of the third law. Action, reaction. So there you have that. Okay. Here's some questions to ruin your self-esteem, make you feel bad about yourself. All right. Make sure you can answer every one of these. What is a force? Make sure you can answer that. What's the difference between force and pressure? Make sure you can answer that. What three things is force measured in the British system? I didn't cover one of them, but it's there in the slide. So go back and find out what it is, because I expect that you know these things because you're an American and you live here in this society and we use these units all of the time. What is pressure measured in the British system? What is weight? I expect that you know that. What is inertia? I expect that you know that. What does it mean to be when forces are said to be balanced? What is a good projectile weapon to have in the case of a zombie apocalypse? I'll give you a hint. Think Daryl Dixon. Okay. All right. So let me move this down here. Let me get out of this. All right. So that's it for this Google slide presentation. All right. And go this out. And namaste. And remember to enjoy your apocalypse.